The second half of the talk today, we're going to talk about elasticity and deformation. And the first part of that is to understand the definition of elasticity. This is actually a stress diagram which shows a relationship between the change in length on this axis and the force applied on this axis. And in the first aspect, you see a linear relationship in which Hooke's law applies, which I'll talk about in just a second. Then, as the degree of force increases beyond that, it begins to not obey Hooke's law, but still is continuing to stretch. This is called the elastic region, which we'll talk about in a minute. Then, as the force continues to increase, you see a greater and greater deformation that occurs, which is permanent, and then ultimately there's a fracture. So the concept of deformation is the fact that anytime you apply a force to an object, you're going to cause that object to change its shape in some way. And deformation is that change in shape that's due to the application of force. Elasticity is a term which means that as long as you're in the elastic region, then the object can return to its original shape after a period of deformation. And so the first two parts of this curve represent a region where the object will stretch or increase in length, but once the force is discontinued, then it will return to its previous length. Hooke's law is a law that states that the degree of deformation is proportional to the force, which is why this first aspect is a straight line with a positive slope. And here's a mathematical statement of Hooke's law, which just says that the change in length or degree of deformation is equal to the applied force F divided by the proportionality constant K. So let's look at this situation in which we are increasing the length of something by means of the application of force, and there's something that helps us calculate what that change is. Now, what this is supposed to demonstrate is these first two are the same material, but one is thicker than the other. And so you have a greater change here with the same weight or force. The second is that this is a different material, so its change is different because it's a different material, even though it has the same thickness, or cross-sectional area is a more appropriate term, than this. Now there's a term called Young's modulus, which is the proportionality constant that relates force to deformation. And the formula for calculating deformation is shown here, where y is equal to Young's modulus, F is the applied force, A is the cross-sectional area, and L, 0, is the original length. Tensile strength is the degree in which a material deforms with an applied force. So it's a term that's somewhat related to the idea of Young's modulus. That is, the greater the tensile strength, the greater Young's modulus would be. Now, what this shows is the fact that the last slide looked at the change in length in this direction. This actually looks at what happens with compression. So the first one, A, is tension, where the rod is stretched when the force is applied parallel to its length. The second is compression. The same rod is compressed by the forces with the same magnitude but in the opposite direction. So let's take a look at a problem taking into account Young's modulus. So let's read the problem. Consider this suspension cable supporting a gondola. The span is 3 kilometers or 3,000 meters, and the diameter of the cable is 5.6 centimeters. How much, or what is the deformation, or what is the degree of stretch of this cable if the material in which the cable is made of has a Young's modulus of 2.1 times 10 to the 11th newtons per meter squared, and the maximum tension during this crossing is 3 times 10 to the 6th newtons. So let's see how we would do this problem. The formula is that the change in length is equal to 1 over Young's modulus times the force applied divided by the cross-sectional area times the original length. Well, the original length is 3,000 meters. The cross-sectional area is pi r squared. The diameter of the cable is 5.6 centimeters, so the diameter is 2.8 millimeter, or 2.8 centimeters, or 2.8 times 10 to the minus 2 meters. And this, if you do the math on this, it equals 2.46 times 10 to the minus 3 square meters. The force applied, the maximum force applied, is 3 times 10 to the 6th newtons. And then Young's modulus is 2.1 times 10 to the 11th. Now, at this point, all you have to do is plug all this stuff in. So that's 1 over 2.1 times 10 to the 11th times 3 times 10 to the 6th divided by 2.46 times 10 to the minus 3 times 3 times 10 to the 3 meters. It's actually 3.00 times 10 to the 3 meters. And if you do the math here, delta L is going to equal 18.0 meters. So the total potential change in length is 18 meters. Now that seems like a lot, but if you look at the fact that that's 18 over the total length of 3,000, it's really right about 5. If you take that as a percentage, it's only about 5% of the total length. And you might not even notice that. I mean, you do notice when you're in these cars that they do sag a little bit, and that's exactly why that happens. Okay, another aspect is something known as stress and strain. This is a typical stress-strain curve for a mammalian tendon. The 3 regions of this curve are called the toe, linear, and failure region. So the initial, or toe, is here, the linear is here, and the failure region is here. The stress is the ratio of the force that's applied over the area, cross-sectional area of the object in which it's applied. The strain is equal to the ratio of the change in length to the total length. So as in that previous example, the strain that was applied to the cable would be equal to 18 meters divided by 3,000 meters. The stress would be equal to that total force which was 3 times 10 to the 6 newtons, divided by 2.46 times 10 to the minus 3. Now here's something called shear deformation. Shear deformation is when, instead of going up and down, it's when you are at a perpendicular to the long axis of the object. So shear deformation has to do with the change based on when you're perpendicular to the long axis of a particular object. It's the sideways stress on a material caused by an applied force. And the sideways here, I think the best way to think about that is the fact that this is generally in the short axis or in a perpendicular to the what would be considered the length of an object. And the shear is called delta x as opposed to delta L, which is in the same or parallel direction. Now delta x is equal to 1 over s F over A L0. Now it's kind of interesting here. This has a very similar look to it than the previous formula that we had, except now we're talking about a perpendicular move and we're talking about a different quantity here. That quantity is called the shear modulus. Now we're going to work a problem, and here's the long axis, and the length is considered that part that's outside that is actually under the shear stress. So it doesn't include the whole length of this nail, but only that part. So delta L is this part. X is the part, the change in from its original, and notice that this change is perpendicular to this length. Okay? So the question is, if you hang a mirror or hang a mass on this nail, and this is the change, and the diameter of the nail is given here, the shear modulus is this, then what is the mass of the object that was hung upon on this nail? Okay, in order to work this problem, we have to start out with our equation, which was delta x is equal to 1 over s F over A L. But now we need to find this quantity right here, because that's how you're going to get the mass. So you have to rearrange this equation such that F now equals SA over L0 delta x. And if we put our numbers in there, S was 8 times 10 to the 10th. A is pi r squared again, so pi, and in this case r is 7.5 times 10 to the minus 4, and then the change in x was 1.8 times 10 to the minus 6. It was 1.8 micrometers. And all of this divided by 5 times 10 to the minus 3, which was the length here. So if we do that, we end up with 51.0 newtons. Now the question asks for mass. So if it's 51.0 newtons, the mass is going to equal 51.0 divided by 9.8, or approximately 5.2 kilos. Okay? So now we've talked about Young's modulus, we've talked about shear modulus. There's one other modulus that has to be taken into account, and that's called the bulk modulus. And that occurs when in 3 dimensions. If there is an inward force on all the surfaces of a 3-dimensional object, in this case a cube, its change in volume is proportional to the force per unit area. Force per unit area is another term for pressure, and its original volume, and is related to the compressibility of the substance. And so, although we're not going to do any problems with this, this is very similar to the last two examples that I showed you. We're going to finish up today with one final review that sort of help you get in mind the kind of question that will show up on the quiz or test. And this is a climber who has a mass of 52.0 kilograms. I want you to find the tension in this rope and the force required in her legs to keep her stationary. Remember, the key word there is stationary. Okay, when we look at this individual, we have to divide her force that's going to keep her up there. We'll call that F net. And that is a combination of the tension in the rope and the force of her legs. And F net, as we know, is equal to F net X and F net Y. And in this case, because she's not moving, F net X has to equal 0, and F net Y has to equal 0. Okay? And so F net Y is equal to the Y component of the tension in the rope, the Y component of the force in her legs, minus her weight. Or these two have to equal her weight. We know that F legs Y is equal to F legs times the sine of 15 degrees. The sine of 15 degrees. So the Y component is the side opposite here, and so it's going to be the Y component of that. We know that Ty is equal to T cosine 31 degrees. Again, here's the tension. The Y component of this tension is the side adjacent to the tension. Okay, that's what holds her up. This is equal to, if you calculate the sine of 15 degrees, you get 0.259 F legs. And this is equal, this is a 2, this is equal to 0.857 T. And her weight is going to be 52 times 9.8, or 509.6 newtons. So we know that if we rearrange this, we know that 509.6 has to equal 0.857 T plus 0.259 F legs. So that's our first equation. Now the X component also has to equal that, and there's only two X's. There's F legs X, and there's TX. Now if we look again at this, TX is the side opposite 31, so that's T sine 31. And F legs X is going to be F legs cosine 15 degrees. Looking at it again, here's her legs. The X component is here, so it's the side adjacent, so it's the cosine. And this is equal to 0.966 F legs. And this is equal to 0.515 T. Now, one of these is to the left and one of these is to the right, or both of them together are equal to 0, either way you want to look at it. So that means that 0.966 f legs is equal to 0.515 t. And let's just solve one of these for the other. F legs is equal to 0.566 33 t. Now we can take this value for f legs and put it right there. And we have 509.6 equals 0.857 t plus 0.259 times 0.533 t. And now we can solve for t. And we get t is equal to 512. And f legs we can also now solve, because we know that f legs is this, and we get 273 newtons. So there's that. Now this was the minimum in order to get her there, so we can use that to find the coefficient of static friction. The coefficient of static friction is equal to f legs x divided by the normal, or the normal is going to equal, and so we know that the normal for her is going to be the cosine of f legs, and so it ends up being f legs x, which is equal to, we calculated that up here, f legs x was the cosine is equal to f legs times the cosine of 15 degrees. And we know that the normal is f legs x times, or f legs times the sine of 15 degrees. Therefore, the coefficient of friction is going to equal these backwards, I'm sorry. This is sine and this is cosine. Sorry about that. It's going to equal the tangent of 15 degrees, which is equal to 0.268